So we have our model. It's called lambda cold dark matter cosmology because it assumes that the missing energy in the universe beyond the 5% that is us is dark matter, which is cold because we want it to clump to form the dark matter outline of galaxies. We said that we are not talking about relativistic particles, but about particles that are very massive when we talked about dark matter, and lambda for the cosmological constant. And this is LCDM standard cosmology, and the problem is solved, right? Not everything. So there are some issues in the study of cosmology, and in another one of the fun parts of this field, the study of the universe at its very largest reduces to a study of the universe at very small sizes because you need to study what is very far. What is very far, you're seeing into the deep past. In the deep past, it was actually very dense. Now, I want to make a point about this past and very dense. The universe in the past was very dense. The universe is flat. We have every reason to assume that it is infinite. One often hears that in the past, moments after the Big Bang, the entire universe was a tiny dense marble the size of a nucleus. This is correct but very misleading. Yes, the entire visible chunk of the universe, the entire 46 billion light years radius sphere that we see today was in fact condensed to something the size of a nucleus at some point. However, that was not the end of the universe, nor is there any reason to assume that it's the end of the universe, any more than there would have been a reason 8 billion years ago for some astronomer to conclude that the universe is only half that size. Since then, our particle horizon has doubled, and we see more of much the same universe. And there's every reason to assume that when we see out to 62 billion light years, we will see about more of the same universe. And what's more, this is also true of someone who lives 40 billion light years that way, and they see an additional 40 billion light years that way. So we have every reason to assume that the universe is homogeneous and isotropic, even beyond what we've directly observed, because otherwise, again, we're putting ourselves in some kind of crazy anthropocentric, we're in the middle of the homogeneous patch, and there's an edge just beyond where we can see. That's ridiculous. So the universe was never the size of a marble. The universe was very dense, but if it's infinite today, it was infinite then. It was just much denser. Off the soapbox. How does the physics of the very small come in? Well, of course, at early times and very high densities, by which time we measure the density not by the redshift and not by the scale factor, but by the effective energy, kBT, of the radiation-dominated universe. So when this energy is above 10 to the 19 GeV, a huge energy. This is in the first 5 times 10 to the minus 44 seconds after the Big Bang. Quantum gravitational effects are important. So this is the vicinity of the singularity. Remember that our expanding universe, if you follow it back, leads to an actual singularity in the relativistic GR equations. Actual singularity in the sense that the curvature was infinite and everywhere in the distant past in this infinite universe. At the Big Bang, curvature is infinite. GR breaks down. A little bit after that, our understanding of physics breaks down because, so maybe quantum gravity will fix the singularity. Even at energies below this Planck energy of 10 to the 19 GeV, or times after 5 times 10 to the minus 44, by the time you reach 10 orders of magnitude higher, 10 to the minus 34 seconds, kBT has dropped down to 10 to the 15 GeV. At that energy, from that energy down, we sort of have a model of physics that works. The standard model determines the physics. We have not made measurements up to that energy. We've made measurements up to 1,000 GeV, but we think that we have reason to understand that the next corrections to physics are suggested at a scale of about 10 to the 15 GeV. Above 10 to the 15 GeV, we think we have reason, theoretical biases, to suggest that, in fact, the electroweak and the strong interaction are part of one grand unified theory. There are various versions of the grand unified theory. They share some common properties, but they would be necessary if you wanted to describe that part of the history of the universe prior to 10 to the minus 34 seconds, and after quantum gravity corrections became unimportant. One aspect of this is that if you try to make a prediction for the value of the cosmological constant, of the vacuum energy from these theories, well, you can build theories in which the cosmological constant is zero. But if you don't build theories in which it's exactly zero, then the typical value for lambda that you find is off by about 10 to the 60. This is one of the largest glaring ununderstood aspects of physics. So this is one problem to which I will not propose a solution today. How to make a cosmological constant that is not zero and is not ridiculously large. Open problem in particle physics, and again, with cosmological applications, but it's in the nature of physics at very small scales to determine this. What are the problems beyond at energies lower than that? Well, there are three famous problems with our scenario. One is that the cosmic microwave background is so isotropic. Well, I thought that was a great thing. It showed us that the universe is really isotropic. Yes, but how did it get so isotropic? See, we computed that 1 degree was the distance a sound wave could have traveled in the 380 degrees, 1,000 years since the Big Bang. Light travels square root of 3 faster. So square root of 3 degrees is the size of a region in the sky that light could have traveled since the Big Bang. So regions in the sky separated by more than square root 3 degrees had not heard from each other by the time of recombination and by the time that the cosmic microwave background radiation that we see was emitted as photons at 3000 Kelvin. So how could the temperature be so precisely equal to within 1 part in 10 to the minus 5 in regions that had not talked to each other? You'd expect fluctuations to cause one region to be hotter and another to be colder, and then heat to flow from the hot region to the cold region until equilibrium. Yeah, but you can't establish equilibrium if you haven't heard from each other yet. So the very uniformity of the cosmic microwave background is a puzzle. We have no mechanism. I mean, you can posit initial conditions that the world was very precisely homogeneous, but that's unnatural. One problem. Second problem is the flatness problem. We measure that today's density is very close to the critical density. The universe is almost exactly flat. Well, this tells you that in prior epochs, the universe was even more flat. In particular, in our dust universe, where, remember, a universe, so ignore the cosmological constant just so we can do calculations. Imagine that we have a critical universe where the only type of matter is dust. In other words, rho of t is rho 0 times a of t to the minus 3. That's what being dust buys me. And so we had this relation that said, well, it defined omega as 8 pi g rho over 3 h squared. So at any time, h squared omega is 8 pi g rho over 3. And in particular, this holds at the present time with omega 0 and h 0. The other relation was that omega minus 1 was this over h squared a squared. So I put the h squared over here. So h squared times omega minus 1 is kr0 c squared over a squared. And now, this is true at all times. So in particular, I can write that h squared omega at any time is the same as 8 pi g rho of t, and this is related to h0 squared omega 0 squared by a factor of a to the minus 3. And likewise, I can write that h squared times omega minus 1 is h0 squared times omega 0 minus 1, except times a to the minus 2. So I have here two equations. If I know h0 and omega 0, I can figure h and omega. It's a little bit of algebra. It's not too bad. And what you find for omega is this beautiful equation over here. Omega minus 1 at any prior time, at any time in the evolution of a dust universe, is related to omega 0 minus 1 by this expression. So what does that tell me? That tells me that if you go back to very small a, in the dim past, then this term is essentially small. This is omega 0. And you find that omega minus 1 is about a over omega 0 minus 1. So omega minus 1 is much smaller than omega 0 minus 1 in the limit when a becomes very small. So if we measure today omega 0 approximately 1 to with some accuracy, say 1 part in 100, then at early times when a was 10 to the minus 18, omega minus 1 had to be 10 to the minus 18 more precisely 1. So again, posit initial conditions where omega, if omega is ever exactly 1, then of course it stays 1. So one possibility is to find a mechanism that makes omega exactly 1. Or posit initial conditions that omega was close to 1 to within 180 orders of magnitude, or find a mechanism that makes that natural. So these are aesthetic problems. There's a third problem associated to these gut extensions of the standard model. They predict that as the universe cools from the gut scale, 10 to the 15 GeV and below, there will be relics left over, magnetic monopoles that are stable and cannot decay unless they annihilate with magnetic antimonopoles, and depending on the extension, various other relic particles. And magnetic monopoles should be detectable. There have been ongoing searches, and we find none. You can predict the density, and we should have seen them by now. So where are the magnetic monopoles? These three problems were addressed by something we'll talk about in the next clip. There's the first problem of the vanishing of the cosmological constant, or the smallness of the cosmological constant, is being addressed by theories of quantum gravity, about which we'll say little. There's a fifth problem, the matter-antimatter asymmetry. The laws of physics are almost but not quite symmetric under the exchange of particles with antiparticles. If they were precisely symmetric, then you would predict that the thermal bath, the hot, dense, early universe, would produce in equilibrium as many particles as antiparticles, as many antiprotons as protons, as many antineutrons as neutrons, and so on. In fact, you might get a small imbalance, but it's important that you get an imbalance, because if you produced equal numbers of muons and antimuons, then when they became non-relativistic, all the muons would annihilate with all the antimuons, and you'd have nothing left. The reason we have something left is because for some reason more muons were produced than antimuons. Now this could be a fluctuation, but then you'd expect that that by and large, maybe you'd have some regions of the universe that are made of matter, where matter predominates, other regions where antimatter predominates, but it's not true. Cosmic rays that arrive from large distances in the universe show us that our universe is almost exclusively made, all the galaxies and the stars are almost exclusively made of protons. There is not a star out there made of antiprotons, although in principle such a thing could exist. Antiprotons could bind anti-electrons and produce atoms where everything is backwards. But that does not happen. In our universe, there is this large asymmetry. All the antimatter annihilated early, and what we're left with is a universe with protons and electrons and neutrons and no antiparticles. This is a problem that's been studied a lot. The conditions under which this asymmetry could be formed using the known laws of physics were formulated by Andrei Sakharov in 1967. The problem is called the problem of baryogenesis. There are many different models. I think the currently favored one is associated with baryogenesis via leptogenesis. You generate an asymmetry in the lepton sector, which leaks into an asymmetry in the production of protons and neutrons. But this is an area of ongoing study, so there are problems in cosmology that are not yet solved. That's fine. Something for you all to solve.